Happy Monday. It's Monday, April the 6th. So this is our third week of online instruction. I feel like I'm getting the hang of it. I still miss going to class. I secretly really want more whiteboards. Every time I'm like, shouldn't I have 3 of these? That would be great. But unfortunately, I just have the one, so we make it work. Let's see. I had a bunch of Zoom calls over the weekend with my friends and family. Katie asks, are you posting the chapter 9 handout today? It will probably go up tomorrow. We are not starting chapter 9 today. So there is a chance we get done early. Or we will just do extra example problems. But the chapter 9 handout will go up probably tomorrow. There will also be I don't want to call it a worksheet, but there's a table that I make that I think will help with some of the chapter 9 topics. So that will go up to tomorrow probably. And so my suggestion is if you don't print it out, because I don't own a printer, but yourself. So it kind of looks like that, but those 2 things will go up today. Keep saying my connection is unstable. I would turn my phone off, but I think I lost it, so I don't know where I put it. Anyway, any other questions? In just a second, I'll give the announcements. There were a couple other things that while we're just kind of giving people some time. So in the weekly update on Friday, I gave a handful of dates that I'm going to see if I can pull up so that I can make sure I give you the right dates, not just what I think they are. So starting today, you have the opportunity to switch into the new grading system through MyWings. April 17th, which is not this week, but next week on Friday, is the withdrawal deadline. So it was last week, but it's been extended 2 weeks. And we do have I think those are the only 2 big changes. Exam 3 is next week, and the final will be 2 weeks later. So I'm trying to think. I feel like there was something else I wanted to tell you guys about the announcements with dates. A couple of things about the grading scale. So what this does is it gives you the opportunity to be a little bit less stressed about Gen Chem 1. Now, I'm happy to talk with as many of you in meetings, pop by office hours. You can send me an email and we can have a private meeting if office hours don't work for you. But the provost email lays out what it is. And it's my understanding that it's A, B, satisfactory, unsatisfactory in the new scale. So you do still need to pass, but it makes the C and C plus change. I do think if you were to earn a B plus, which is an option in my course, it would stay as a B plus. And I will not know if you've selected that. So if you have questions, you can send me an email. I will tell you that right now, Canvas looks like it's doing something a little wonky. So the new online quips are giving weird final grades. I intend to go into today or tomorrow and fix that. I will send an announcement when I do that, or I'll tie it in with the quip update next week. So it seemed like all of you were able to upload your pictures, which, that was just so great. Some of you are great artists. I'm a terrible artist, so I enjoyed that. Likely we will use something similar to that for the exam, where you will do part of it by hand and then you will upload a document. So more details on exam 3 will come this week, and then more details will come the following week. So I'm just trying to give you guys information, but it will be on April 15th. Okay. So announcements for today. So we are going to, Dylan asks, how do you opt into the new grading scale? I think it's on my wings. Apparently I see 2 people saying that it's a button on my wings. That'd be nice. It's a yellow button on my wings. It also indicates there might be one on the Canvas homepage, but it is not through the course homepage. And I believe for the new grading scale, you have to do it per course. So if you're in 6 courses and you want it for 3 out of 6, you can do that. For 6 out of 6, you will have to opt in 6 times, I think. But I don't, again, I have not seen a preview of that. Sebastian asks, can you stay with the current grading scale? Yes. Yes, you can. There should be no change to you. The things in the syllabus still pertain. So I have another student saying they don't see it on Canvas. I haven't, but I know that the provost said it was in my wings. So it looks like it's in there. Okay. All right, so we've got a couple of questions. So if it goes bad, you can get the pass-fail thing. I think so. It is my understanding that it's A/B pass-fail or A/B satisfactory, unsatisfactory with whatever plus minuses I assigned. I'm not entirely certain about that. So Megan is right. We do have until next week. I will also stay tuned for the announcement. There will be a way for you to submit a Google survey if you are concerned about whether or not you need to withdraw. That way I could try to grade your exams faster to give you the data from exam 3. But stay tuned. That is coming. So someone else asked, will the exam be the same time? The same time, an hour and 15. It won't be longer than class. It will be similar. The exam, we'll come back to the exam. I will send an announcement with all of the information and what I think is really clear. But the exam will be somewhat similar to the exams that we used to take. Okay. If we have to upload documents, JC, I have a plan for you because I know that my computer takes like 90 days to upload stuff. I have a plan for all of this. Hang tight. I know that doesn't help you, but right now what I can tell you is it will be through Canvas. It will be open notes. So it will be timed. But there's some other parts of that we're going to do. Now, so if you opt in, it only helps you. To be honest, I can see what Megan's saying about like if you opt in, it's pass fail. Let me do some investigating because both what Sam has asked and what Megan has said are my 2 thoughts on that. And I will investigate exactly what it happens. And I will try to send an announcement this week, today or tomorrow it'll basically be titled something along the lines of new grading scale information. That way, because it sounds like I'll give some generalizations. I think we're all confused about what it is. So that way we can all get the idea of clarity. But if you have questions, you can send me an email about it. You can drop it in the comments box and I will read them, or pop in office hours. I'm happy to help you guys. It is my goal for us all to be successful, and how that's defined is a little crazy. So other information, we do have a quip. It will be similar to last week. It will actually be a quip, not a gimme. The topic is Lewis dots of a molecule. So what we learned today about how to draw something that looks like H2O or methane or PF5 or something like that is what we will do for the quip on Wednesday. It will be like the previous quips, opens at 4:15, closes at 11:59. If you have technical difficulties, please send me an email. I'm happy to help. I will make it longer, even though it should only take you a couple of minutes to complete it. I do know that trying to draw it, take a picture, upload that takes a long time. If for some reason it kicks you out, please send me an email. Attach your quip to that email. If you upload it, I do not need an email, okay? If you're concerned, send me an email, it's fine. Okay, any other questions? Those were all the announcements I had. For Chapter 9, we're gonna do sections 9.1 through 9.6 over the next 2 lectures, or as much of that as we get through. So one part of Chapter 9 will not be on exam 3 or the final. You should see that's going to drop out of your ALEX here pretty soon as well, because there's some stuff we're just not going to get to. Okay, any other questions? I know. You were all waiting to see Lil. Hold on. Here she is. Her favorite thing to do. Oh, man. I don't know if you saw the dog, because now it's saying it's unstable. I'd like to apologize. My internet is tired, like everyone's. But she lays right under the whiteboard and just sleeps. So, okay, from here, we will go back to, we will look at them and then we will work on today's topics. Whoops. So some of the examples that, you're fine, I gave you guys last week were CHCl3, with carbon being the central atom. So the first thing we need to think about is the number of valence electrons, which is 4 for carbon, plus 1 plus 3 times 7, so 21, 22, 26. So from here, the trick is to remember that there are just rules, and whatever those rules are is what we can basically work with. And so the first thing is to count our valence electrons, check. After we count our valence electrons, we want to put the central atom and then connect all of our entities to this. So from here, we've used 2, 4, 6, 8 of our 26 electrons, but we have some left over. So the next thing we want to do is put remaining electrons around the outer electrons, or outer elements, so 2. So now we've used 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we've used them all, but you might be thinking, well, hydrogen doesn't have octet. Well, hydrogen has octet when it has 2 electrons. So hydrogen is filled, chlorine is filled, everyone is filled. From here, we can check that carbon, our central atom, also has octet. So everyone has octet. Now, in last class, we did talk about formal charge. So formal charge is most often utilized in compounds where we see a negative or positive charge overall. And so in this case, there is no formal charge, but you should always check. So the next one that I gave you guys was H2O. But I know if I erase this, someone might still have a question. So next is H2O, where oxygen is our central. You lost sound. Can you hear me now? That's like awkward, and I feel like Oh, sounds like maybe you could try refreshing. I don't really know. But, so when we have H2O, which is water, oxygen is our central atom, and we need to count our valence electrons. So hashtag VE is 2 times 1 plus 6, which gives us 8. So now we need to draw our molecule. So we're going to put our oxygen in the middle, and now we need to connect our 2 hydrogens. So now I put mine top and bottom. You can put them on any of these 4 sides. In chapter 9, we're going to learn what they look like in 3D. So from here, we've used 4 of our electrons. So that means we have 4 left. Both of these hydrogens have octet. And so now we have 2 lone pairs left on the oxygen. So this is the H2O structure for a Lewis dot. So Thomas asks, what determines which element is the central atom? I think in almost everything that you get from me, I will underline it, and I will underline it on the exam. I know it's that way in the worksheets that I give you guys. I don't remember what Alex does, but I try to always underline it or tell you in words, like oxygen is the central atom and everything is connected to that. Ooh, Sarah says it's easy to tell on Alex. So this is the Lewis dot structure for water. So you could have also drawn this. Or any other arrangement of these. They don't have to be across or side by side in a Lewis dot structure. So the next one we have is, what do I write down? SO3 2 minus. So it doesn't look like there are any questions about the structure of water. So we'll go ahead on to the sulfite ion. So the first thing is always the valence electrons. So we have 6 plus 6 times 3. Then we need to add 2 because it's a negative charge. Plus 2, so 24, that's going to equal 26. So sulfur is our central atom, and we're going to have 3 oxygens. The worksheet keys will still be posted 48 hours before the exam, so next Monday, right? Yes, unless you're asking about a different worksheet key, Katie, then send me an email and I'll post it. The chapter worksheets keys will still go up right before the exam, but I may try to push it back a little bit further so you guys have more time to look at it. So I'll try to do it this weekend. So for sulfate or sulfite, we are going to put our sulfur in the middle, connect our 3 oxygens. Again, any arrangement of this is fine. And so now we've used 6 of our electrons, so we have 20 left. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12, 14, 16, 18, 2. 8 plus 8 plus 8 is 24. Let's add 2 left here. So now we have, everyone has octet. We've used all of our valence electrons. And so the question becomes, from here, we have a Lewis dot structure, but we need to look at formal charge. So all of our oxygens look the same. So the formal charge for oxygen is going to be 6 minus half of the bonding electrons minus all of the lone pairs, which is -1. So now we have a formal charge of -1 here. So the formal charge for sulfur is 6 minus half of the bonding electrons, 2, 4, 6. Whoops. Minus its lone pairs, which gives you +1. So the overall charge on this molecule is a -2 because these two cancel and these two are negative. Now, you may have also seen another structure. So I'm going to draw that in red so that we can see overlaid what that would look like. So if instead we added a donated double, we took this lone pair and made it a double bond here, the formal charge for sulfur would go from 6 minus half of 2, 4, 6, 8, minus 2, which is 0. The formal charge of this ion, O red, would be 6 minus half of 4 minus 4, which is also 0. Now, I know that one question you might be having is, but now sulfur has more than octet. In, I don't know, 15 minutes tops, we will talk about why this is an allowed structure. For now, this is an allowed structure. This is actually what we would call a preferred structure. So sulfur keeps its lone pair because the oxygen, the red oxygen, had a lone pair and it needs to go here. Otherwise, oxygen would have 10. So oxygen can only ever have 8, but sulfur can have more than 8. Now, we're going to talk about this again shortly, but I want to show you that there is more than one. The other thing with this is that there are resonance structures of this. No. So the previous one was a structure. It is a non-preferred structure because every element in it has a negative or positive charge. However, we can create this structure, which is resonance, by using a double bond between oxygen and sulfur, where now sulfur and one of the oxygens, the red oxygen, both have no formal charges and only 2 of the elements have formal charges. So this is an option. We will talk about this more and when we get to slide 20, which is where we're going to start on here in just a second. And this is one of the exceptions to the octet. So you can have odd numbers, less than octet, and more than octet. There are reasons why some elements can have more than octet, but we will continue to talk about that. So from here, I'm going to start to talk about slide 20. Which is 8.7. Once I find my paper. So for the next few moments, I want to talk about elements who violate octet. So up until this exact moment, I really told you it's octet or die. It turns out that there are some elements, a lot like hydrogen, where they don't always get octet. And so, or there's a lot of different ways. We can classify our exceptions to the octet into one of 3 groups. Octet, we mostly want octet. Here are the 3 ways that you can violate octet. So the first thing is molecules, yeah, we can see this, with odd electrons. So usually when we tabulate total of our valence electrons, what we see is it's some multiplicative of 2. Every now and again, we encounter molecules, not very often, where there's an odd number of electrons. So I have said, and I do mean, that electrons do not like to be alone. These molecules, they are alone because that's how many valence electrons there are. But it's super rare overall. So some examples would be ClO2, where Cl is chlorine, NO, and NO2. Now we are going to look at NO. You can try these on your own if you would like. So for NO, the number of valence electrons is 5 plus 6, which equals 11. So right away we know that there's going to be a single lone electron. So when we have this molecule, we're going to the best. So we can set up our 11 electrons by starting with nitrogen. If we use 6 electrons here, 8, 9, 10, 11. So from here, we know that this isn't going to work. This has octet. This doesn't have anything close to octet. So we're going to create this, where everybody has, so nitrogen has 2, 4, 6, 8 for octet. Oxygen has 2, 4, 6, 7. That's not great. Not bad either. But let's think about if we put, instead of the lone electron on oxygen, what about if we give it to nitrogen? So we still have the same 11 electrons running around. But the question is, which of these two structures is going to be preferred? It's going to come down to formal charges. So formal charge is one of those things where we have to do it more often. So on most of these molecules, looking at the formal charge is something that we should do every time. So for the first one, the formal charge of nitrogen is going to be 5 minus half of 4 minus 4. So 5 minus 2 minus 4, negative 1. The formal charge of oxygen will be 6 minus half, 4 minus 3. So that gives us a plus 1. So we have a negative and a positive. So already this should kind of give you the, your chemical intuition might be saying, I don't really like this. So there's 2 things that you shouldn't like. We don't really like molecules where both sides have charges, but it's always a bad idea for the more electronegative atom to have a positive charge. So oxygen here has a positive charge and nitrogen has a negative charge. So this is possible, but it's worth exploring what does this one look like. So the formal charge of nitrogen in this molecule is 5 minus half of 4 minus 3, which is 0. So anytime we can get a formal charge of 0, that's fantastic. But for oxygen, it will be 6 minus half of 4 minus 4, which also equals 0. So the fact that this structure has no charges and this structure has charges tells us that this one is the preferred structure. So it is preferred because this one has no formal charges where both atoms have formal charges on the first one. So I'm going to give you guys a second So if you have any questions, you can go ahead and ask them. I think the chat box is on that side. But if you don't, in just a second, we're going to talk about molecules where an element has less than octet. I need a new marker. So we know that hydrogen's octet is two electrons. So hydrogen has a full set of electrons when it has two, because this is the 1s orbital is totally filled. So you can have a totally filled orbital with 2 electrons. It turns out that there are a couple other elements that can also have less than octet. To be honest, it's not that many. So if we look at BF3, where we have 3 valence electrons plus 3 times 7, that gives you 24 valence electrons. I'm not gonna lie, I've had that thought too about trying to learn some hard math through YouTube Live. Yeah, I would make more other videos if this was a lot of math, but it's not. It's mostly drawing. I'm sorry. I didn't cause this pandemic. So let's talk about BF3. So we can put boron in the center, put our 3 fluorine molecules. So once we add octet, or all of our valence electrons, we are going to have, so we are on slide 20.2. So it basically has 3 dots on it. So the first dot was the previous one. This is our second dot. And then we'll talk about the next one. So BF3, boron trichloride. So if we look at this, the fluorines all have octet, but boron doesn't. So we could try to draw a structure. But before we do that, let's think about the formal charge. So the formal charge for boron would be 3 valence electrons minus half of 6, which is 0. Ooh, that's good. For fluorine, it would be 7 minus half of 2 minus 6, which is also 0. So a preferred structure has no formal charges. So boron, and any element in the same column as boron, aluminum. Hold on, let me get a periodic table. So any of the elements in this column can have only 6. Well, they only have 3 valence electrons. So anything in this column can have less than octet. So this less than octet less than octet for elements in in the column with boron. So aluminum, etc. And so the reason this occurs for minimization of formal charge. So what I'm saying here is that 4 elements in the same column as boron, and only those. So if you were to think about sodium chloride, which doesn't make list dot structures because it's an ionic bond, not a covalent bond, but we know that sodium only has 1 electron as a valence electron. When it creates a complex, it does not get octet. So we can see that in this case. So less than octet really only happens for elements in that column. That's it. So everything else should have octet. So hydrogen, boron, aluminum, gallium, indium in that column. Everything else wants to have octet. Well, other things like to have octet. So any other questions before we look at molecules where an element has more than octet? Kind of like the sulfite ion we looked at the beginning of class. So in some cases, the central atom can have more than octet. So central atoms with more than octet which it turns out really can only be 10 electrons, or in rare cases 12. With more than octet are what we call hypervalent. Now, hypervalent reminds me a lot of, I have some friends who are super flexible. You know, the people, I'm not going to do it because mine don't bend that way, where they go like this and their fingers like bend all the way back. They're hyper flexible. So hypervalent central atoms basically say they can hold more electrons. They can hold more electrons sometimes. So these elements also are localized in certain regions of the periodic table. So this does not occur for second period. So these must have access to d orbitals. So n equals 3 or greater. So if you were looking at your periodic table, I know this is not the best idea. So anything in this column, fluorine, oxygen, nitrogen, they can't become hypervalent. They're too small, kind of like oxygen. But for elements like phosphorus, sulfur, chlorine, anything from here down and here over. So if you want to make a box there, those are the ones that can have more than octet. Everything else, it's octet or less than octet. So if you're looking in the P block elements, the first row has less than octet. This top row only ever has octet. And down here in this section, they can have 10 or 12. Not like 100, just 10 or 12. It's okay. know this is not the best. So anything in N equals 3 from phosphorus over to argon all the way down this column. So this over here, not this over here. So anything in N equals 3 on the far side of the P block can have access to this. But here's the other thing. You're going to know that they have access to that because they will have extra electrons. So most of the time, these don't. So Warren asked if it includes the noble gases. We will see that sometimes the noble gases can start to be involved in compounds. But the other thing is when we make these compounds, they will have so many electrons that they will have to have hypervalent central atoms. So let's look at some examples. Oh no. Okay, hold that thought. While I type the definition in the comments box, if you are here, go ahead and, if you're up to date, go ahead and try to draw something for PF5. I know we can go back, but this is just as fun. So hypervalent. Oh, you can't see over my big head. Copy it out. Oh, one more thing. Well, that is not how you spell orbitals, but you get the impression. So let's think about phosphorus pentafluoride. So right now we know that phosphorus is going to have 5 things stuck around it. But let's think about our valence electrons. So the valence electrons here, phosphorus has 5 plus 5 times 7, which I believe is 42. So from here, we're going to follow the same rules that we've seen previously. So we're going to plot phosphorus in the center, add our 5 fluorines. So now we're going to nope, there's only 40. Thanks. Math is not my favorite today. So when we put our valence electrons around fluorines, years later, so now we've used all 40 of our valence electrons. So the thing with hypervalent is most of the time we're going to see this, where phosphorus is definitely connected to 5 things, which means that it has to have more than octet because there's 2, 4, 6, 8, 10 electrons around phosphorus. So we should double check our formal charges. So formal charge for fluorine would be 7 minus half of 2 minus 6, which is 0. For phosphorus, 5 minus half of 10, which equals 5. So all of our formal charges are 0 in this molecule. So I'm going to give you some other examples. ICl4 minus, where iodine is the central atom. But I think what we're going to do is you can try this one, I don't want to say on your own, because we'll do it at the end of class, but I would definitely like to finish the rest of the chapter 8 material so that you can definitely finish your ALEX objectives. So we will pick up this one at the end. Feel free to give it a try. And if we don't, I will do it first thing on Wednesday. But for the next, I don't know, 15, 30 minutes, let's finish talking about chapter 8, and then we're going to pull back in that last part of chapter 5. So the last thing we kind of want to think about, so now we're on slide 21, is the strength and length of bonds. So we've kind of talked about this a little bit before, but I'm going to give you guys a second because I feel like if I erase the So one thing that we know is that some bonds are stronger than others. So we know that a triple bond is stronger than a single. We also know shipping stores definitely print. By the way, I think there's a way that you can get stuff printed and mailed to you, but I don't know that for a fact. I also don't own a printer. UPS. So a triple bond is stronger than a single. If you look on slide 22, which is a table, so I won't draw out. We will look at 3 different carbon-carbon bonds. So the carbon-carbon single bond is 1.54 angstroms. The carbon-carbon double bond, I'm sure you guys can still see this, is 1.34 angstroms. And the carbon-carbon, getting close to the bottom, triple bond is 1.20 angstroms. You do not need to memorize these numbers. I'd give them to you, or anything else you need to know. So I just put my hair up, but we'll take it back down. So if we imagine that this is a single bond, it's pretty flexible, but if you tie it, I made a double loop. You can kind of shove my fingers in there, and we can see that it's a little bit tighter. And so it's a much smaller bond, or a much tighter circle. Now, to make a triple bond, you can see that there are 3 rubber bands mixed together, but I'm afraid I'm going to shoot this across my house. If you try to stretch it, I'll be honest, it doesn't stretch. We all know this. So the thing is, bond lengths are about the same. A single bond is going to be longer, and what we're about to find out, easier to break because it's longer than a triple bond. It turns out that a triple bond has 3 times the electron density. So you could imagine that it will take, not always, but almost 3 times the energy to break it. So now we're going to, if you vaguely remember, which maybe you don't, in chapter 5, there was section 5.8, and I said, we're going to talk about that later. So on slide 23, you'll see bond enthalpies. So now we're going to talk about the last way to calculate delta H of reaction. So if you remember, vaguely, delta H of a reaction is how much energy it takes to go from start to finish. So regardless of what start to finish it is. So, my bad, sorry, screwed up my hair. So bond enthalpy is the energy required to break a bond. So if you think about Legos, I know I don't own any Legos or I'd show you, but the energy it takes to put it together is opposite for the energy it takes to take it apart. So bond enthalpy is the energy required to break or form a bond. So bond enthalpy is always positive. You have to put in energy to break a bond. So what this is saying is you have to put in energy in order to break a bond. See if closing the blinds will help. I see. So bond enthalpy is the energy required to break a bond. We're going to start calculating delta H, which is the heat of the reaction, using the bond enthalpies. So if you look at slide 25, we're going to come right back to 24. All of these bond enthalpies are provided for you. It will be like the delta H not F's. I will give you that information on the exam, or Alex has it buried in its tables. So if we think about calculating delta H of reaction, so delta H of reaction, we can start to use Hess's law. Now, you might remember Hess's law as the way that we could manipulate equations, which is true. But what Hess's law also stated was that if you could measure the other, like 3 of the 4 sides of a square, you could extrapolate the 4th side or determine that algebraically. So if we know that we have CH4 plus chlorine, and we want to create HCl and a methane with just 1 chlorine, we're going to start to be able to use the bond enthalpy for this. But the whole point and the whole issue of this is that we want to be able to take this apart to make this. So the bond enthalpies would so delta H of reaction is going to be broken minus formed. Now, you can't see that at all. So, broken minus formed. It is the only delta H where it's not products minus reactants, because delta H is always positive in what I will provide you. So in this case, we're going to break 1 chlorine, and 4 carbon hydrogen. And then we're going to form one hydrogen chlorine bond, one chlorine carbon, and 3 carbon hydrogen. Now, in the table that you will be provided on an exam or on slide 25, we can read off of that the value that it is required for any of these. So a carbon hydrogen single bond is worth 413. And so we can see that a carbon chlorine bond is 328. A hydrogen chlorine bond is 431. A single chlorine bond is 242. Now, when you plug all of this into your calculator, and we're going to do another example up on top of the board so it'll make a little bit more sense, we're basically going to determine that delta H, I'm going to write this at the top, delta H for this reaction is going to be negative 104 kilojoules. So this is just a new component. 328. So this is useful when delta H naught F is not provided. So for like a new molecule. So the reason we didn't talk about this in chapter 5 is because all of the questions ask you to draw the molecule, which we've just learned how to do. So you can imagine that Alex will say for this compound and then give you like Cl2 or CH4 and tell you what the products are. And so you'll have to draw the molecule and then figure it out from there. So if we look at slide 27, which I'm going to draw up here. So for a delta H reaction example, so the example is if we have 2 ethane molecules plus 7 O2. So this should look like a combustion reaction. Add, break up, add. Yes, so it's delta H is the sum of the broken, so the reactants minus the products. Forms, what do we have? 4 CO2 plus 6 HOH. Yes, so to calculate, need more space, not a problem. So delta H for the reaction is going to be the sum of the bonds broken minus the sum of the, you're fine, bonds formed. Hey, so Sarah, if you got 517, did you remember to multiply some of those numbers by the quantity of the bonds that were broken or formed? So in this case, we're going to sum up what bonds are broken and then what bonds are formed and then subtract those. So broken. Now, in this molecule, we can see that there is a single carbon-carbon bond. But we know that because there's 2 of them, we have 2 carbon-carbon. there's 1, 2, 3, 4, 5, 6 carbon hydrogens. Multiply by 2, so 12 carbon hydrogen. And then 7 oxygen-oxygen bonds. Now, it's important to make sure when we scroll back to the table, which I'm going to look at, to pull our values, we can now say what these values are. So for the carbon-carbon bonds, it's 2 times 348, 12 times 413, this is from slide 25. And then for oxygen, it is oxygen, which is 495. So when we plug all this into our calculator, this gives us 9,117 as our broken. Oh, I'm glad you guys got it. For the formed, we have, so now in this molecule, there's 2 carbon-oxygen double bonds, multiplied by 4, which is 8 carbon double bond oxygen. Here in water, there's 2 OH bonds times 6, so that gives you 12 OH. So a carbon-oxygen bond is 799. And oxygen-hydrogen is 463. So when we total all of these up, we should get, yeah, you can read it. 11,948. So hi, Ronnie. So delta H, can you see me far right there? Yeah. Reaction is equal to 9,117 minus 1,948, which gives us a final value of negative 2831. Man. Hold on. So in this case, it's always going to be bonds broken minus bonds formed. These numbers here are on slide 25, or Alex has them, or on the exam, I will give it to you. It would be just like on exam 2, where it would say like, using the heats of formation provided in this way. So this is the last topic for chapter 8, because it also comes out of chapter 5. So does anyone have any questions? Otherwise, we can draw a few more Lewis dot structure examples before I let you guys go a few minutes early today. So Katie asked the topic for the QUIP. So the QUIP topic is on drawing Lewis dot structures. I didn't think it was the ones for this weekend, but it's possible that I've screwed up the Alex objectives. But I will double check. It should be the objectives that are due on Thursday. I will double check. I think you worked ahead, which is never a bad thing. But yes, it is just like we do it on Alex. I will double check on Alex. but the quip is drawing Lewis dot structures today. So yeah. That is true. Alex does do stuff slightly different than the way I do. Both ways are correct. Both ways will get you full credit on the exam. So here are examples that no one can see. Yes, I will do the ICL4. Alex does make its own rules. Kind of a mess. So the iodine ICL4 minus so the valence electrons in this case is going to be 7 plus 4 times 7 plus 1, which gives you 36. So for ICL4 minus, we put the iodine in the center. We're going to put our 4 chlorines out on the edges. So that we make sure we can see all of those and no one can see if I stand in front of the board. So in this case, we're going to go ahead and add our octet out here. So we've now, if we count up for each of these, we've used 8. And so 8 times 4 is 32. So that leaves us 4 electrons left over. So those remaining 2 go on to the iodine. Now, iodine can accommodate up to 12. So if we look at this, we can see that all of the chlorines have octet. Iodine has 2, 4, 6, 8, 10, 12. When we go hypervalent, 12 is the max. You can't just throw more electrons in there and make it like 86 or something else. It's 8. You can basically have 6, 8, 10, or 12. 8 is the dominant structure. So here, the thing is we want to double check our formal charges because somebody has a negative charge. So the formal charge for iodine and the formal charge for chlorine. Now, you could calculate it for all of the different chlorines, but when we look at these, could you put them on like here and here? That's also acceptable. I just like them on opposite sides. You can put them as long as your 2 pairs of electrons are anywhere. Yeah, you could put your 2 pairs here and here, here and here, here and here, anywhere you like, as long as you have 2 pairs of electrons, no lonely electrons in this case. So in this case, we want to check the formal charge of chlorine, which would be 7 minus half of 2 minus 6, which is 0. For iodine, it would be 7 minus half of 8 minus 4. So 7 minus 8 is -1. So our negative charge resides on the iodine charge, or on the iodine molecule. Let me check my... So there are some examples that no one can see, so I will rewrite them in just a second. Does anyone have any questions about the... Hey, Katie, it might be that my Mac is like old, but whatever you asked if I have to draw just showed up as a box. and I don't know what the box is. If someone else can see it, feel free to comment. Oh, do you have to draw brackets? No. So in this case, because we know that the negative charge resides on the iodine, we can just put the, thank you. You can, so there's no need for brackets. We can just put the negative charge on the iodine. The brackets are more of a general statement of saying like, hey, there is a negative charge somewhere, but we don't know where it is. In this case, we know that it is. Good question. Other questions today? Oh, this is about our way to do that. We could just tilt it up a little bit and then you guys can see the stuff at the top. So here are just some other examples for you guys to, and it looks like we have enough time to do one of them. So we have aluminum trichloride, arsenic tribromide, and sulfur hexafluoride. So here are 3 different ones that we can all look at. So these 3 items are just different ways that we can determine, or these are just different molecules. Today, it probably still feels like, okay, I don't really see what's happening. I get that, but the next part of chapter 9 is all more drawing. So the Lewis dot structures will become easier the more of them that we draw. So let's work on one of these. I'm going to do the arsenic tribromide first. So AsBr3. So arsenic has 5 valence electrons plus 3 times 7. So 21 plus 5 equals 26. So from here, we can put arsenic in the center. So I put my 3 bromines at 90 degrees to everyone else. So now we're going to start putting our valence electrons around. So we're going to put 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 4. So we've used 24 of our 26. So the last 2 valence electrons, why are you multiplying by 7? So 7 is the valence electrons on bromine. So I didn't necessarily multiply by 7, but there are 3 bromines, and so we need to account for the valence electrons in all 3 of those. So from here in this molecule, we've used up all 26 of our valence electrons. We should verify that everyone has octet. 2, 4, 6, 8. So all of our bromines look good. For the arsenic, 2, 4, 6, 8. It also has the correct number of, it has octet as well. Okay, any other questions? All right, well, since you guys are still here, oh, we only have 1 minute left. In that case, go ahead and try the aluminum trichloride and the sulfur hexafluoride on your own, but we will draw those. They may not be the first things that we draw on Wednesday, but we will draw them this week. The chapter 9 handout will be posted sometime tomorrow. The quip is over drawing something like this. So these are 3 examples for the quip topic on Wednesday. It will open right after class. it will be a draw something and upload your picture of that, or you can complete it on your iPad or another way. Ooh, Katie asked a good question. Aluminum has less than octet. What do? You just draw it. So the aluminum trichloride would look like this. You would just draw the aluminum trichloride in this way, and there's no need to indicate that it doesn't have octet because the formal charges are all 0 on this molecule, so you can just draw it just like this. Any other questions? Not a problem, glad to help. So we finished all of the chapter 8 material. We will start chapter 9 on Wednesday, and we will get as far as we get before exam 3. Miss you guys, and I will see you here next week. Feel free to come to Zoom if you have questions or stop into Megan's SI sessions. Bye, guys.